And still, it takes a knowledgeable physicist with long experience to understand and to explain in a simple way what is happening with our climate and what are actually the opportunities. What can we do about it? It's not enough that we are just listening when our Earth will going to go bad, but what can we do about it? How can we prevent it and make a better future for the future generations? And that's why it's my great pleasure to introduce our next professor of physics, Pascal van Ypersele. He comes from Université Catholique de Louvain, and he is also he's been with IPCC for a long time. I think he's been vice chair. He is honorary member of the Club of Rome chapter in Brussels and member of a lot of international committees. But what we really want from him today is to explain us what we can do in the future to make our climate better. Professor van Ypersele, the floor is yours.
Thank you very much. It's really an honor and a pleasure to be here this morning and to speak to you about climate change in a room where exactly 2 years ago the IPCC was meeting, by the way, for the election of the new bureau. Actually, today is a special day, not only because we are here at this very important conference, but because there are a number of anniversaries that we could celebrate. And one of them is this one. Yesterday, actually, was exactly 60 years ago that the first artificial satellite was launched, Sputnik 1. And for a number of weeks sent those famous beeps, beep, beep, that the entire world could listen. And of course, this is very important because it's the beginning of the space age. And 40 years later, another satellite was sent. That satellite Cassini, sent in October 1997. With a long mission, and that's to go to Saturn and ultimately to crash over there and to take many pictures and do many studies and measurements on the way. And this is a beautiful picture of Cassini, taken by Cassini when it was 3 million kilometers away from the planet Saturn. Why do you think I'm showing you this morning? Because the same satellite, shortly before crashing, took this picture. You recognize the planet Saturn and its rings, but you also see a small dot there, a very small dot, a blue dot. It's actually our planet. And you see from that distance 1 billion 0.44 kilometers from the Earth how small we are in the universe, how fragile we are in the universe. This is also, in a sense, shown by this picture, which is a picture taken by Apollo 17 in December 1972, one of the first pictures showing the planet as a whole, showing also, which has been photographed many times afterwards, how the atmosphere of our planet is thin and fragile. This is a picture taken in 2013 by astronauts on the International Space Station, showing one of the 16 sunrise and sunsets they see every day as they circle our planet. And you can see how thin our atmosphere is, how fragile it is. And so is our climate, actually. And so is our ozone layer in the stratosphere. But a few days ago, some good news were published about the state of the stratosphere and its ozone layer. And this is also coming from a satellite. It's coming from the Copernicus. You heard a lot about the EU research programs this morning from Maria de Carvalho. Well, Copernicus is a European program for the observation of the Earth that integrates many data from satellite, but also from models. And they announced a few days ago that the state of the ozone layer is actually has stopped to degrade. It has not really started to improve yet. That's too early. It will take a few other decades. But at least, as you can see, the size of the ozone hole, which is the blue zone there, is smaller than when the first SDEWES conference was organized. I don't think it's an effect of a SDEWES conference. This is an effect of the Montreal Protocol that decided at the end of the 80s to forbid the production of the CFCs, the chlorofluorocarbon, which were understood to destroy the ozone layer. So a few lessons from that ozone story. The atmosphere is fragile, and so is our climate. Understanding it is crucial because it's thanks to research about the processes linking the emissions of chemical compounds by human activities and the state of the stratosphere that it was understood it was essential to prevent the degradation of that very important layer of gas protecting us from an excess of UV radiation to cut those emissions. It also allowed humanity to understand for the first time clearly that human influence can threaten the global habitability of the planet. But it also showed, and this is the good news, that determined action decided by humans can actually reverse the degradation of our environment and climate, and also put us on a more sustainable development pathways. And in a similar way as the move away from CFCs opened opportunities for companies and many actors to benefit from the need to transition away from those CFCs and use new techniques, new products to deliver the same services. There are many opportunities that were associated to the fight to protect the ozone layer, but there are many opportunities associated to the fight against climate change. Now, I have shown you many pictures of the planet. The planet itself is actually a piece of rock in the universe as well. So the problem is not so much with the state of the planet. It is much more. What's much more at stake is what's living on the surface of this planet. And Professor Sloos mentioned this morning in his opening speech that humility and compassion was needed. And when I think about climate change, I have compassion for those kids I met little more than 2 years ago in the countryside in Kenya. They had been affected by severe drought, but they were recovering their smile because of the efforts to adapt to climate change in their region and to promote irrigation, for example, to allow agriculture to take place, even in those very dry conditions. But many other people in many other regions are affected by changes in climate and variability. I mean, look at those floods just a few examples. Those floods in Germany in 2016. A few days ago, look at what happened in Puerto Rico, where millions of people today are without electricity, without clean water, without food, without access to communication. I mean, it's the worst humanitarian crisis that the US has known for decades. Now, you might think, well, we're not living in Puerto Rico, we're not living in Machacos, this is very far away. I know many of you are living in Germany, but this is very far away. We are in Dubrovnik, so Dubrovnik is safe, isn't it? Well, this was 3 weeks ago in the historical part of the city. On September 11, 2017, here in Dubrovnik, what happened? Torrential rains and floods. And this came after 3 months, I was told this morning, of drought. So climate is changing. Well, not everybody is saying that. Some are pointing to the fact that there has been a so-called temperature pause over the last 15 years. Well, it's actually a very selective choice of information, because if you look at the last 100 years, you could find many periods where you have a so-called pause for a decade or a little more. Climate is actually defined over a 30-year period, and when you look at the whole record, you see how lying with statistics is easy if you take only 10 or 15 years of temperature data. Clearly, the trend is upward, and the global temperature is increasing. Because there are that kind of controversies around the climate issues, the UN created the IPCC, the Intergovernmental Panel on Climate Change, just 30 years ago. Again, another anniversary that will be celebrated next year. It was created in 1988. And the IPCC was created not to do research, additional research on climate change, but to do something that's even more original in a sense, and that is to assess in a very rigorous and objective way the state of knowledge about all dimensions of the climate question, the scientific aspects, the technical aspects, the socio-economic aspects, how to fight climate change, how to adapt to it where you have no other choice. And the IPCC works with all countries of the world, produces reports every 6 or 7 years, the so-called assessment reports, which are produced in a very rigorous way with 3 cycles of writing, review, rewriting, associating hundreds of authors. The last report had 831 and 31 lead authors from all over the world. And I hope many of you, if you are not already, will become in the future lead authors or contributing authors to IPCC reports. The IPCC has produced many assessment reports since the first one in 1990, but it also produces thematic special reports. For example, and I took just a summary of that report here, it produced in 2011 a special report on renewable energy. The key questions the IPCC, which received the Nobel Peace Prize in 2007 for its work together with Al Gore, half of the prize for Al Gore, half of the prize for the IPCC as an organization, are the following. What is happening in the climate system? What are the risks? What can be done? And I will try to highlight some aspects of those 3 questions. But I know I have too many slides, I know I have too many things to say, and you will have my slides afterwards, so if I go a little fast on some of them, you can revisit them with more time. Knowing that I have too much material, I will start with 4 key messages emerging from the 6,000 pages in the last report, 6,000 pages. Hopefully with summary for policymakers and synthesis report. And this is the synthesis report of the last IPCC report. You can find all of this on the IPCC website. I'll give you the address at the end. The first key message is human influence on the climate system is clear. The second is continued emissions of greenhouse gases, the gases that trap heat close to the surface of the system, will increase the likelihood of severe, pervasive, and irreversible impacts for people and ecosystems, such as the impacts we saw. I gave you a few examples a minute ago. While climate change is a threat to sustainable development, there are many opportunities. You see the word opportunity there. Many opportunities to integrate mitigation, how to reduce emissions, adaptation for the part of climate change you cannot avoid anymore, but also, and that's very important, also you can integrate the pursuit of other societal goals. For example, this was not written because this was adopted in 2014, a year before the Sustainable Development Goals mentioned by Professor Slaus this morning, were adopted at the UN 2 years ago. So it means there is a way to fight climate change or to adapt to climate change in the context of pursuing the 16 Sustainable Development Goals. By the way, objective SDG, Sustainable Goal number 13, is related to climate action. In a nutshell, and this is the last message which summarizes the others, humanity has, and I use italics for the word has, because it's very important the present tense is used, has today the means to limit climate change and to build a more sustainable and resilient future. Now, some details about some of those key messages. First, on climate change. Look at the temperature data. You see the year in the middle, the months around, and you see with time how the temperature is increasing and getting close to the 1.5 temperature limit and 2-degree temperature limit which have been adopted as the ultimate goal of humanity in terms of climate protection. The last 3 years, 2014, 2015 shown here, and 2016 have broken the temperature record at the global scale. And as you can see, the warming is pretty well distributed in the world and is stronger overall over the continents than over the oceans because of the thermal inertia of the water. Now, there are many other signs that climate change is changing because the temperature, global temperature in particular, is something that's very abstract. For example, sea ice cover is decreasing. You see it has lost 2 million square kilometers over the last 30 or 35 years in the Arctic. Glaciers are receding. Look at this picture taken by a US glaciologist in 1961 in Alaska. And from the same viewpoint in 2003, you see how the ice has melted. This is the behavior of most glaciers in the world, and this is adding water to the oceans also. What's also adding water to the oceans is the melting of the ice sheets in Greenland and Antarctica. And you see, and this is again coming from satellite data, you see the decrease in the mass balance from the Greenland ice sheets every year, losing 200 billion tons of ice on a net basis, which becomes water added to the ocean, which is another factor in addition to the melting of the glaciers and the water expansion for this sea level rise, which has been observed over the last 100 years, about 20 centimeters. It's also in the ecosystem area that changes are happening. For example, in many parts of tropical oceans, coral reefs are dying because of the heat, also because of the acidity, but mostly because of the heat. Why is all this happening? Well, mostly, as I will try to show you in a minute, because of this, because the CO2 concentration in the atmosphere has increased by 40% over the last 250 years, which is a period since over which the Industrial Revolution took place. I'm not going to spend much time on this to remind you that without greenhouse gases, we would have a very cold temperature. We would probably not be here to talk about it, minus 18 C. And we should be very thankful that water vapor, CO2, methane, and other greenhouse gases actually trap much of the infrared radiation radiated by the planet so that instead of -18, we have on the average approximately +15, which is much more favorable to life. But CO2 is really changing significantly, and you see that when you stand back a little bit and look at what happened over the last 10,000 years. For 9,800 years, the CO2 concentration, the amount in the atmosphere, was pretty stable, of the order of 260, 280 parts per million. But you see the explosion since the Industrial Revolution, when we started to use, on a massive basis, coal, oil, and gas. If you stand back even more, you see that even if you look at the last 800,000 years, almost 1,000,000 years, how do we know that? By looking at the ice and the air trapped in that ice in Antarctica, shown top left. You see that never the concentration has been higher than approximately 300 parts per million, and we are at more than 400 now. So why is this CO2 concentration increasing? I will spend a little more time on this diagram in the next one, because I think it's important to understand key elements of the carbon cycle, which is not as well known as the greenhouse gas and the energy diagram. You see here, before perturbation by human activities, the two large loops from natural system. First, vegetation and forest on the left, and second, ocean. You see arrows and fluxes indicated or labeled in billion tons of carbon per year, gigaton of carbon per year. If you want to have that in CO2, of course, we have to multiply it by 3.7. And you see that overall, natural systems emit together 190 billion tons of carbon per year, but they also absorb, they recycle the same amount. Vegetation by photosynthesis, and the ocean by dissolving CO2 in the colder part of the oceans, while the emissions from the oceans are mostly taking place in the warmer parts of the ocean. The reason for that temperature effect is summarized by the so-called Henry's law, which says that the gases dissolve better in colder liquids than in warm liquids. So even though the fluxes are very important, 190 billion tons per year, the amount of carbon in the atmosphere, the pre-industrial amount, was 600 gigaton of carbon. And that amount, as I've just shown you, has been pretty stable for the last 10,000 years. Now, we are changing that. We've been changing that for the last 250 years by burning coal, oil, and gas, and also deforestation. For example, which is just to illustrate the point, for the last decade of the 20th century, we were emitting a total of 8 gigatons of carbon every year, of which a small half, a little more than 3 gigatons, were found and measured in the atmosphere as added every year. Why 3 only added to the atmosphere every year and not 8, which is what we emit? Because nature renders a wonderful service to humanity by recycling what we don't recycle ourselves, actually, and by recycling more than one half of what we emit. But unfortunately, it is not able to recycle more than that one half, which means the other half accumulates year after year in the atmosphere. And that's why the concentration of CO2 in the atmosphere increases. And this is also exactly the reason, and it's extremely important to understand that, while we don't need to reduce emissions by 20 or 30% or 40% or 50% or 60% or 70% or 80%, we need to reduce emissions to zero as quickly as possible. I repeat, to zero, because too few people are really aware of that, as quickly as possible, just if we don't want the climate problem to accelerate and to become worse. Now, you might say, are you really sure that it's really CO2 and the other greenhouse gases that are causing that climate change? Yes, now we are pretty sure. This is the observed temperature curve, which you have seen already, and we have tried to reproduce this curve with modeling studies, climate models, which capture all the physics and all the chemistry that we know is happening in the climate system. The blue curve is the average of all the simulations obtained with those climate models where they are forced only with natural factors, because natural factors influence climate, namely small changes in solar activity and volcanic eruptions. By the way, if Mount Agung in Indonesia erupts, which it might do in the next few days or weeks, we might see a cooling effect for 2 or 3 years, as we had in 1963 when Mount Agung, the same Mount Agung in Indonesia, a big volcano there, erupted. And you can see the decrease in temperature that took place then. The red curve is obtained by feeding the climate models with, of course, the natural factors again, but also the human factors that influence climate, mostly greenhouse gas emissions. And as you can see, at the times of the assessment report number 1, AR1 of the IPCC, the blue curve was not able to get very close to the observed, but climate scientists and statisticians are very cautious, so they wrote in 1990 at the time of that report, we will not detect univocally the effect of human activities on climate before another decade. Actually, it started to become clearer in 1995 at the time of the second assessment report, and then it spoke about discernible human influence after 1950. And then things became clearer and clearer, and the last conclusion from the last IPCC report in 2013 is that it's extremely likely, a probability of over 95%, that human influence has been the dominant cause since 1950 on the warming. So now that we have established that, we can look at the future. And we have to work with scenarios. For example, scenarios for the CO2 concentrations. And you see in particular a very low scenario which stabilizes the concentration at the present value, approximately 400 ppm, and a very high scenario which leads us in the 22nd century to concentration that would be at least 4 times higher than today. If you feed those scenarios to climate models, this is what you get. Of course, for the lowest scenario, you get a lower increase than for the highest scenario. For the lowest scenario, you get a temperature increase of the order of +1 degree above the present temperature. The present temperature is already approximately +1 degree above the pre-industrial. So, the bottom, why? Because I'm touching something I shouldn't touch, sorry. The bottom blue zone shows you that with the so-called RCP 2.6 scenario, it is possible more or less to observe the objective of the Paris Agreement. But if we stay on the business as usual scenario, the other scenario called RCP 8.5, which is a scenario on which we are now, we could get between 3 and 5 additional degrees. It means 4 to 6 degrees above the pre-industrial. And you might think, well, is this such a bad news? Why is it so important to avoid that? Well, to try to show you why, I'll show you this image of the planet as it was 20,000 years ago. Of course, it's a reconstruction, but based on solid geological observations. And what you can see, of course, the clouds have been removed, is that on North America and Europe and Siberia, there was a very thick ice sheet, which is not present today. Of course, we have an ice sheet on Greenland, but we don't have anymore an ice sheet in North America and Europe. That ice sheet was so thick, 2 to 3 kilometers thick, that the ocean level on average was 120 meters lower than today. Why do I show you this? Because the difference in temperature between that planet 20,000 years ago and the planet we know today is only, in terms of global average temperature, 4 to 5 degrees. And it took approximately 5,000 years to gain those 4 to 5 degrees. So a change of 4 to 5 degrees in a century, which is possible if we stay on the business as usual scenario, and of course average temperature distributed in space, it would mean much more, as you can see here, in some parts of the world, for example, in the northern part of Europe, with temperature increase in excess of 8 or 9 degrees, would be a huge threat to the habitability of the only planet that is inhabitable on a large scale in the solar system. So maybe we should think a little bit about that. And there are billions of people who are going to be affected in many ways if we stay on that scenario. It's not only temperature which is changing, it's also precipitation patterns. And one aspect of precipitation patterns that's very important is that with increased warming, you have more evaporation on the surface of the oceans, and you have the intensity of rain, as shown here for Europe in winter, DJF is December, January, February, the intensity of rain increases. And the kind of events we had in Dubrovnik on September 11, I didn't say it was caused by climate change, but I'm saying the probability, and the IPCC is saying the probability of that kind of events is strongly increasing in a warmer climate. Now, sea level is also due to increase by 30 centimeters to 1 meter by the end of the century. And this is going to affect, again, millions of people. Just think about the Nile Delta, for example. The red zone was, and this is from 2001, a region where 10 million people were living in the red zone, which is just 1 meter above the level of the Mediterranean we see outside. So those, even if the sea level rise is only 0.5 meter, it's millions of people who will have to find another place to cultivate and to live. But it's also ocean acidification, which results from the absorption of CO2 by the oceans. Because remember, natural systems absorb half of what we emit, and actually the oceans absorb a quarter of what we emit globally. And this is, unfortunately, it's a law of chemistry. You cannot do much about it as long as the emissions continue. This is contributing to acidifying the oceans, which is, as you can imagine, not very good for marine life and for shells, which are made of calcium carbonate, sensitive to acid. And look at this reconstruction of the acidity level, the pH, over the last 25 million years to put the change we are heading to if we don't change our pattern of global emissions. It's a real shock compared to the changes in acidity in the last 25 million years. So the impacts of climate change are already underway from the tropics to the poles on all continents and on the ocean and in the ocean, affecting rich and poor, but a common rule is unfortunately that, as always, the poor are more vulnerable and more affected by the same phenomena. I'm not going to explore the entire range of impacts and show you with other examples why this is so challenging, but these are a few examples of areas showing why this is a huge challenge for humanity. This is to illustrate the fact that vulnerability is, of course, higher for poor people. This is from the streets of New Orleans at the time of Katrina in 2005. It's clear that that poor person, which is handicapped in addition, is more vulnerable to the same event, the same floods in the city, than a rich American who was able to leave the city. So the IPCC tried to summarize the severity of the risk and the increase in risk for different temperature level. You have to look at the right temperature scale on the right, which has a 0 at the pre-industrial time. And you see that when you enter, when you are above 1.5 or 2 degrees, you are clearly in the red zone with high additional risk due to climate change for at least 2 of the main reasons for concern. And I don't have the time to explore all the details here. But this shows that there are many reasons to try to do everything possible to be as close as possible, or even below, if that was possible, to the RCP 2.6 scenario, which is shown here again, than to stay on the high course we are on right now. Now, to realize the challenge even more in terms of emission reductions now, and maybe link what I spoke about to what you are doing in your disciplines and during this conference at the core of the nexus between energy, water, and food, I think it's important to understand this diagram as well. This is a diagram that was very new in the last IPCC report, showing an almost linear relationship between the temperature increase, which is the vertical axis, and the cumulated emissions on the horizontal axis. Actually, this linear emissions stands for the future as well, for the 4 scenarios considered in a very broad way. Of course, there are uncertainties around that line, but overall, it's a linear line. Why is it so important? Because it means that if you want, for example, not to go above 2-degree warming, at some point, of course, there is some uncertainty, agree. At some point, you cannot add to that cumulative emissions. In other words, the emissions need to be reduced to 0. Because if you move to the right on that horizontal axis, inevitably, you will move up on the temperature scale as well. And this is the idea behind the so-called carbon budget. You probably have heard about these numbers, showing that to stay with a probability higher than 66%, which is not such a high probability, by the way, you would have, under a 2-degree warming threshold, which is one of the thresholds agreed as important by the Paris Agreement, you would have to respect a total carbon budget of 900 billion tons of CO2. But we have used 2/3 of that budget already. So only 1,000 billion tons were, at the time of the report, based on data stopping in 2011, remaining before we cross that line with a probability of 66%. So we could be very careless and say, okay, we'll continue and we'll see, because after 25 years, if we emit 40 billion tons per year, we have used entirely the 1,000 gigaton budget, and we will see what happens. Well, there's something clever to do, and that is to try to distribute that budget another way and to peak as soon as possible and then decrease the emissions, and you can use the same budget and still respect the temperature target. And this is what is shown here. So it is possible to design scenarios touching energy issues, mobility issues, household, industry, electricity production that fit that pattern. And these are quotes from the IPCC report. It means reaching 0 or even negative emissions before the end of this century. So that's the challenge, is to get to 0 net emissions for CO2 and as many other greenhouse gases as possible. I spoke almost exclusively about CO2 because CO2 is 80% of the problem as far as climate is concerned. The other gases play a role. They need to be managed as well, methane, N2O, etc. But CO2 is really the main thing. So where can we reduce those emissions? What are the key areas highlighted in the third volume, the volume dealing with mitigation, and this is a summary of this IPCC report dealing with mitigation? Well, you have a list here. The priority number 1 is energy efficiency, and priority number 2 is low or no carbon energy sources, and renewable energy, of course, play a very important role. In terms of sectors, these are potential highlighted in the previous IPCC report, but I still like this picture because it shows the importance of action in the building area. It shows the potential on the 2030 horizon for emission reductions at using least cost strategies. But it also shows, and the color relate to the regions of the world, but it also shows that if you put a price on the fact of using the atmosphere as a dustbin for CO2, the motivation to decrease emissions and look at what happens in the industry increases. So it means economic instruments are very important to motivate, and changes in financial patterns are important to organize and to achieve that energy transition. Here, you see the changes in investment pattern assessed by IPCC Working Group 3, the working group dealing with mitigation. And you see how per year the increases in funding for energy efficiency and renewable need to be at the world scale for this 2 degrees C scenario to happen. And of course, it would be even more so for the 1.5 degree target. There are many co-benefits in protecting climate. And one big area, but it's not the only one, where co-benefits can be delivered is in the reduction of air pollution, which deliver huge health benefits because there are millions of people suffering today from bad quality air in so many cities of the world. If well-designed, measures to prevent climate change could offer so many opportunities in so many areas: air pollution, health benefits, employment, energy security, food security, improving gender equality, etc. There are so many areas where you can have benefits in the climate area, but also so many benefits if the measures are well designed in those other areas. And this is why integrating climate action in the context and in the framework of the Sustainable Development Goals and this objective to transform the world in that direction that the UN has decided 2 years ago is so important. And of course, there are opportunities in integrating research, such as the research that is done by all of you in each of your disciplines, but also across disciplines in a meaningful and policy-relevant way. And this, to work well and be really policy-relevant, would benefit also from cooperation with social sciences in general. So the Paris Agreement, concluded 2 years ago as well, is providing now the international framework for all climate action. I'm not going to explain everything that's in the Paris Agreement. It's a very complex agreement. But just to highlight the 3 objectives, and these are quotes from the text. Okay. These are the objective of the Paris Agreement. So to achieve, to hold the increase in global temperature well below 2 degrees while pursuing efforts to stay 1.5. So it's a bit ambiguous, typical of some UN languages for them. It is language sometimes, but this is the compromise reached. It's also increasing the ability to adapt to climate change. And the third objective is making finance flows consistent with the 2 other objectives. And it's written in the Paris Agreement in a very convoluted way that actually the goal that's in the middle is to achieve 0 net emissions. It's not written that way, but the language there means exactly that, which was the language, the notion highlighted in the IPCC report. So getting an agreement in Paris was very important, but now, as the Secretary of the Convention said at that time, the real work starts because it needs to be implemented. And every delay, of course, because of the cumulative nature of the CO2 pollution, increases the risks of dangerous climate change. Now, Paris is a first step. As you can see, if you were staying on the business as usual scenario, it would be on the top line there. And the blue zone, the blue trajectory shows the 2 degrees C scenario for the coming decades. The green trajectory shows the 1.5 trajectory. And you see INDC, there are those 2 rectangles shows the sum of the announced efforts by countries in the framework of the Paris Agreement where they lead us. It's better than to be in the top line, but it's still far from what is needed. So we will have to work very hard in the coming decades, and the help of scientists from all disciplines will be extremely important. I'm not going to spend time on this, but you can read it later. I'm trying to show that I'm trying to walk the talk in my own personal life with my wife. We spent a lot of time over the last 2 years improving our home to get to zero carbon in a way. I want to spend maybe 20 seconds, if you allow me. I'm almost done for my conclusions and last advice. A very important opportunity is now, before October 27 this year. You can, if you are interested, nominate yourself. I mean, you have to talk to your national focal point for IPCC. You can nominate yourself, and you can see who is your national focal point by going to the IPCC website to become an author for the next assessment report. The deadline for the nominations is at the end of this month. But there are also opportunities to contribute as an expert reviewer. Again, this comes regularly, but check the IPCC website. Of course, publishing research is very important. My conclusions: the challenge is huge. I've heard this many times. But addressing it opens so many opportunities as well. It also opens economic opportunities, opportunities to address in a synergistic manner other societal goals, such as the 17 SDGs. Last but not least, addressing this challenge together will allow us to look our children and grandchildren into their eyes when they ask us at some point, what have we done, how we have contributed to avoid the disaster that was announced otherwise. There's a Buddhist saying that my wife reminded me this morning, which says this, and this complements very nicely the two virtues that Professor Slaus mentioned in his talk, which were humility and compassion. Courage is the gateway to happiness. In a nutshell, yes, we can. Thank you very much for your attention.
Thank you very much for your illuminating and passionate presentation, and also thank you for leaving time for questions. I'm sure there are many questions. Yes?
This is Professor Birol Kilkis from Başkent University, Ankara, Turkey. First of all, I would like to thank for this very insightful and very clear message-holding presentation. Thank you so much. My question is, you have indicated that energy efficiency is one of the most important factors in decarbonization, so to speak. I agree. But to the extent that I can see, the exergy or the rational use of energy resources in a balanced way in terms of the quality of energy is not still included in IPCC reports. Am I mistaken? Or because if I am mistaken, that's fine. If I am not, there's a large room in front of us as an added probability to reduce the carbon dioxide to a much faster extent simply by using the energy as rational as possible at the right time, the right energy resources, at the right proportions, etc. That's my question. Thank you.
Thank you very much for your question. Absolutely. I'm sorry if I gave the impression that only energy efficiency was important. It was listed, coming out from many studies, as the key priority, but it doesn't mean it's the only priority. Actually, just next to that priority, the next one is increased investment in renewable energy and more generally in low carbon and no carbon sources of energy, even to a certain extent where it's accepted, and of course we know it's controversial in many places, nuclear energy as well, but certainly not as the first priority. But actually, yeah, using as little energy as possible, because the cleanest energy is the one that you don't use, and the one that we still need to be produced as cleanly as possible. Absolutely.
Next question.
Michael Walmsley from New Zealand. Some countries, like New Zealand, have agricultural emissions from animals as one of their largest contributors. In the ICPP reports, is there much talk about changing of diet to where we become less dependent on animal food products as a strategy for reducing emissions?
Thank you for your question. Actually, it's also an area that is discussed in the IPCC report and which is part of the many options. There isn't a single bullet to solve the climate problem. That's very clear. I mean, for ozone, the ozone layer, which I explained at the beginning and which could inspire the courage we need to have in climate, it was relatively easy because just by changing CFCs to substitute, we could deliver the effect we wanted. For climate, it's much more complicated because we have CO2, but we also, as I mentioned, have methane, which is one of the gases emitted by agriculture and livestock production in particular, but also by rice cultivation. So there are many ways to reduce and to address the different emissions, and indeed one way, which is discussed in the IPCC report, is and assessed on the basis of scientific literature, is changes in diets in the sense of reducing meat intake, which has also, by the way, according to many specialists, health benefits. And it helps also to reduce the associated emissions due to livestock. Now, there is also research, as you probably know much better than I do, research on how to change the manner in which livestock is fed to reduce emissions as well. So there are different opportunities in that area, and that is also assessed in the IPCC report.
Next question.
Would you please comment also on chlorofluorocarbons, which has direct effect to stratospheric ozone depletion? Like, what are the measures and what are the precautions to reduce them? What are the sources?
Yeah, thank you. Well, as I mentioned in the beginning, actually CFCs, the chlorofluorocarbon, are now essentially forbidden in terms of production. There's actually a big difference between the Montreal Protocol, which is focused on protection of the stratospheric ozone layer, and the climate agreements, is that in the Montreal Protocol, it's the production of CFCs which is prevented. It was first prevented in developed countries, and there was a few years later, it was also forbidden in developing countries. But the difference with the climate agreement is that in climate agreement, what is controlled is the emissions, not the production, which means that there are still avenues in the CFC area to help the environment by making sure that in every country in the world, the products that were made 30, 40 years ago with CFCs are recycled in a way that prevents the emissions of those CFCs in the atmosphere. I don't know how old are the seeds you are sitting on, but they might contain CFCs. They might, if they are 50-year-old. They're probably not, but they might, because CFCs was used also to produce this kind of foam and etc., the small bubbles inside. At some point, probably not these ones, they contained CFCs. And when those products, imagine these would contain, this foam would contain CFCs. If they are dumped without any precaution, then slowly the CFCs would finally reach the atmosphere. So there are still avenues to reduce that, but otherwise, and it's the same for refrigeration systems which were using CFCs. It's very important that the CFCs from those systems, from those old systems, is recycled. But there are no new systems using CFCs because substitutes have been invented and are now used with much less effects, or almost zero effect on the ozone layer.
Next question.
In the meantime,
Yes,
just
I'm sorry.
point to this slide, which I skipped if you have an opportunity, go and see the latest movie by Al Gore, because it's very good. I saw it a few days ago, and it's very good. An inconvenient sequel. Yes, next question.
Yes, 1 and 2.
My name is Smile, and I'm a PhD student of the Aarhus University Sustainable Energy System Group. So you introduced very nicely this very interesting scenario, RCP 2.6. So the way I understand this scenario is that we have to start reducing our CO2 emissions in 2 years from now on, 2020, and eventually reach negative emissions by the year of 2080. Well, I have a hard time understanding this. So I would like to hear your opinion how plausible this is for humanity to follow this pathway. Thank you.
Well, thank you for the question. Actually, I started my talk with some optimistic information related to the stratospheric ozone layer, and I wanted to start my answer to your question with some optimistic information as well, which I haven't had the opportunity to deliver yet, and that is that over the last 3 years, not only the temperature has reached peaks, successive peaks, but global emissions have apparently reached a peak as well. So over the last 3 years, the last 3 years for which we have statistics, the global emissions have stopped increasing. So we may have reached a plateau. Now, 3 years is a bit short to be sure this is the case, but apparently, one factor is the move away in China from coal usage, not only for climate reasons, also for air quality reasons, the co-benefits aspects, is starting to have an effect, and the context, the Paris Agreement, the context of the decarbonizations, the movement towards, too slow, but still, the movement towards decarbonization seems to have probably started. Now, it's of course not enough, because if we stay at the same level, given the cumulative nature of the carbon cycle, which I spent some time to explain, we will still increase the concentration in CO2 and then continue to increase temperature. But there are ways to decarbonize deeply, and actually there should be in this room people who are much more specialized than I am. I'm a specialist of the climate system. I'm a climate modeler than I am. But in the literature assessed to produce the scenario RCP 2.6, it was shown that using a combination of all the most efficient techniques in all areas, buildings, electricity production, mobility, diet changes and other behavioral changes, etc., it was possible to decrease emissions to zero before the end of the century, and also to reforest, for example, which helps to recapture some CO2, or to use carbon capture and storage technology associated with the use of biomass. And if you think about it, if you produce electricity with biomass which has absorbed CO2 from the atmosphere, and if you burn that biomass, which of course is going to release CO2, but if you prevent that CO2 to reach the atmosphere because you capture it and you store it, which is not easy and which is expensive, etc., but still, technically it's possible, you can actually produce, quote-unquote, negative emissions, because you artificially remove CO2 from the atmosphere. It can help in a transition period. It's not going to solve all problems, but it might help to do a little part of what is needed. And it might, in particular, help to get those negative emissions which are needed in some, at least, of those RCP scenarios, RCP 2.6 scenarios.
Last question.
Hello, thank you for your interesting speech. I would like to ask a question. What strategies other nations should use when a country doesn't want to obey Paris Agreement? Thank you.
You know, thank you for your question. The key to the success of the Paris Agreement was its voluntary nature to a large extent. So there was a common agreement, almost universal. Well, you know that some country, but this country is pretty isolated at the moment, doesn't want to participate anymore, but the rest of the world is moving despite what that country wants to do. And part of that country is actually acting very fast, as if the climate agreement was applying to it. But so there was a common agreement about the goals and the framework. But if there was a universal agreement, or almost universal agreement in Paris, it was also because countries didn't feel they were pushed too strongly by other countries to do something they didn't want to do themselves and to decide themselves. So there was a subtle balance between constraints by peer pressure and voluntary nature, which is, of course, a big weakness. So there's a big strength in the Paris Agreement, that it's the overall goal, the framework, the common approach, and the fact that it's basically universal. But there's also a big weakness, which you pointed to, and that is voluntary. Now, one important element to know about the Paris Agreement, there are many, but let me give you one more, is that there is an ambition cycle mechanism that is part of the agreement, which says that every 5 years, all countries of the world are invited to revisit their commitments, their nationally determined contributions in the UN jargon, in the light of the IPCC report. So there will, for example, be an AR6, maybe some of you will contribute to that report, published in 2021, 2022. Well, the Paris Agreement has scheduled already a review of the commitments of all countries of the world in 2023. And countries are invited to reconsider and to see, well, is what I've proposed in Paris in 2015, is it high enough? Is it good enough? Can I do better? Shouldn't I do better? Or maybe the knowledge about possibilities in using new technologies will evolve, and there is an opportunity to improve the Paris Agreement every 5 years and to raise its ambition, which clearly will be needed. As I've shown you, the collective effect of the first commitment period of the Paris Agreement is far from what is enough, and there will be opportunities to move those rectangles in the future closer to either the blue or the green line.
I know there are still many questions, and we are lucky that Professor will stay with us for lunch and he will answer all our questions. And now it's time to thank Professor for his clear presentation, and I hope he motivated a lot of you to apply for the expert.
Sure. Of course, you'll have all my slides afterwards, either on my webpage, which is here, or on the organization webpage. So the second webpage there, under conferences, you will find my slides, let's say, tomorrow if everything goes well. But they might also be on the organizers' webpage.